Alright, so I'm uploading some code onto Canvas so that you can have working code. And the idea here is now that you've gotten to play with a bit of the code and you've got your frustrations and the things you have to search out, we're going to take some working code and use it. So the code that I have here um, is code I use to show direction curves. And again, this is going to be up on Canvas, and this is the MatLab Octave. And so what I want to look at is the sections of the code. And what I have is my min and max x values. I have step sizes in x and y, and the mesh grid. And I have my function defined, my differential equation defined. And I have it defined in terms of p and t, with t being the independent variable and p being the dependent variable. And what we're going to do here is we're going to use this to plot solutions. But for right now, I'm just going to work on the direction field. So the thing we do is I'm going to show you what this code is doing right now, and then we're going to change it to do other things. But the idea is whenever you want to start new code, you come back to this file and just change the things you need to change. You don't have to rewrite it all over again. So what I'm going to do is I'm going to click up here in the file and run, and we get my output. We get my solution curves and we get my direction field to this differential equation. We can see that there is a terminal velocity at 8, and we can see things above 8 converge towards this. Yeah, so it's a good example with direction fields match our solution curves. And so down here in the plot, what I did is I gave space for 7 different solutions. I want to comment them out. And so you put a parent sign in a percent sign in front of a line, and it changes color here. And what that's saying is it's a comment, and so it's not running. And so I'm going to come back here and this is save file and run. And now I just have the direction field. And so this file can do multiple things for me. I can look at solution curves. I can look at direction fields as needed. So what I'm going to do is I'm going to go to the textbook and I'm going to look at the solution curve for, what's an ugly one? I'm going to look at the solution curve for the p times p minus 1 times 2 minus p. It's number 7 in exercise 1.3. Actually, I want to do the t cubed minus x cubed. This is number 8 in section 1.3. And so that has dx dt. So I'm going to make a comment up here to note what I'm working on. I'm working on dx dt equals t cubed minus x cubed. Now, I've already set up all these functions to work with p and t. So I just have to make aware that t is my independent variable. So t dot cubed and x dot to the third. Right? Because t is my independent variable and p is my dependent variable in this case. And here x is my dependent variable, t is my independent variable. So just translate between the functions. And so now I've created this function that's cubed. Now one of the things to note is I put dots before operators with vectors to make sure it does the vector multiplication properly. I don't know if I overkill it or not, but it has been working for me. And what I'm going to do is I'm going to begin. I don't know where to look for this. So I'm going to start with negative 5 on the x-axis to positive 5. So I'm changing my x values. And I think I'll do the same in my y values. I don't know if it'll help me or not, but that's where I'm going to look at this function. And then we'll go from there. I haven't even looked in the book yet. I'm going to keep the step size the same, and for right now I have enough information. I'm going to see if the vector field works. I'm exploring a new function. I don't know much about it yet, so I'm just going to look and see what I get running it. Well, I okay, I get a direction field. I see I have this zip line running up through it. But I've got a behavior. In fact, it looks like the behavior will look really neat right in here. I can kind of see quartic things running through. So we can look at it here. And so the question says if a particle is located at x equals 1 when t equals 2, what is the velocity at this time? So it looks like we can find out what the slope is when t equals 2 and x equals 1. And so we could plug that into the differential equation on our command line here. So let's see, my diff EQ, oops, Q, and what did I want to give it? I wanted to give it 1 for y, 1 for x, and 2 for t. And I get -7. So I have the slope coming back in. So notice I have my function loaded, and I can interact with it on the command line if I need to. And if I want to, I can interact with it in the editor, and I can get my direction field. And so now I worked with this new differential equation. I can pull out values for it. And what I'd like to do here now is I'd like to graph a solution. So I want to open up my direction field again, and I want to look for a particular solution I want to see. I'm really interested in this kind of swirling effect going around here. And so I think I'm going to say, hey, what happens if I start at 0 and I'll do a couple values above and below 0 on y. So notice how I'm using working code to explore a rather odd differential equation. So I come down here, and I'm going to look at 5 solutions. So I'm going to grab 5 solutions, and I'm going to grab their plots. And I want to look at what happens if we're above 0. So I'm going to go 3.0 as my initial value. 1.0. And I want to look at them at 0. And I want to look at them symmetrically below 0 as their starting initial x values. And I don't know what this is going to do, but I'm using my working code to explore. And I hope I typed everything in correctly. And I'll run. And notice I get these values. They're kind of anything that starts at 0. It's kind of running up through here. I also have something really odd going back here on the -4 side as it's trying to plot through. So it looks like these very steep lines on -4 are causing an issue, and I might need to look more closely between -2 and 2. And notice if I go back and think, oh wow, I'm not seeing much here, that these are very steep slopes. And so this is has a very steep solution set there. So I might need to look closer around areas I want. So let's go do that. Let's come back here. I'm going to say that I'm going to look between 1 and 0. So I'm going to narrow the solution curves I'm going to look for. Let's see, that's going to be 0.5 and -1. So there's the symmetry there. I'm going to come back up here, and I'm going to change my minimum. I'm going to do between 1.5 on either side of the axis. Origin, I should say. And so notice I'm playing with this differential equation. I'm not asking many other questions of it other than what do you look like and what do your solutions look like. And so if I narrow in on it here, I get these answers, which is showing a lot more happening around 0, and this weird swirling pattern that happens around the origin for this particle. I kind of don't like the scale of things here. These isoclines got big, so I'm going to decrease my step size. So I'm going to say I'll make it 1/8 instead of 1/2. And we'll see what that does. See if I can get a better feel for what's going on here. And yeah, I got a little more behavior. And so now I'm exploring this differential equation and I'm seeing what it can do at different starting values as we graph it. And so by having this working code, I can now explore functions and I don't need to rewrite code each time. I can come back and I can say, well, you know what? All right, I'm done exploring this equation. I want to go back to the velocity that I was looking at. So this is being a velocity and time of a particle. I'm going to look at between 0 and 10, right? Because time only moves in 10. Or not 10, positive directions, time's only positive, sorry. And I'm going to look between negative 10 or negative 1 and positive 1 on the y's, and I'm going to make up a model. I'm going to say, hey, we had 1 minus v cubed over 8 So what happens if we bring this 8 down to 2? Remember the cube root of 8 was the terminal velocity, so will the cube root of 3 be the terminal velocity? That's what we thought would happen. Let's see if it happens. So that should be enough to get something. I changed my max and mins. Let's see what it does. We might have some problems, but we'll change them if need be. Ooh, created a lot of points, I think, with this going up to 10. It might crash on me. That happens sometimes. Sometimes when I film it, maybe the video will skip. That does look like I'm running way too much here. So maybe I'll have to increase the size here. So let's bring these back up to a quarter. And, ooh, did I crash out my editor? No. Oh, yes, I did. I have a syntax error here. And what happened? Oh, look. That was supposed to be to the third power. Oh, that's good. So let's see what we get here now. Now it's running, but I still get an error. Oh, yes. See, I made that mistake. But making mistakes are good. Alright, it's not V, it's P. All of these are functions of P. There we go. And so when I changed my differential equation to be P cubed or V cubed divided by 2, here's my new differential equation. And I'm not getting the behavior I thought I was getting, so I need to explore this a little bit more. But I now have something that I can use to explore my differential equations. And so once I have this one piece of working code, I'm going to keep using it until it doesn't work for me. And so any solution I do from now, I'm going to run to this piece of code. All right, laters.